Next we'll start with triadic Koch curve. We'll see the diagrams so that you can understand better. Please refer the Google Classroom for notes. So what is triadic Koch curve? We know that it's a curve, and what is the method to draw it we'll see. Now to draw a triadic Koch curve, we have to start with a basic line segment. Now first, in the last video we saw what is Hilbert's curve, and we know how to start drawing Hilbert's curve. It is to be done by drawing 4 squares or 4 quadrants and then connecting the centers, right? And then we go on doing the same in every approximation. Now in triadic Koch curve, we have to start with a line segment. Then we divide that line segment into 3 equal parts. We can see in figure 2, right? First is original line. Second is, we call it as the first approximation, where we will divide the line into 3 equal parts. Next, now first after drawing the line and dividing into 3 equal parts, then we are replacing the, we can say that we will replace the central part or central third part, that is the above one, by 2 adjacent sides of an equilateral triangle. Then this gives us a curve whose end coordinates are same of that of the original segment which we have drawn, but here we have built it in 4 equal length segments, right? You can see in the image. Now each 1/3 the original length. So now new length of the curve will be 4 by 3, right? 4 equal segments and 1/3 of the original segment. So the new length of the curve will be 4/3 of the original segment. Now we have to repeat this process for each of the 4 segments. We can see in the figure second, that is where it is written first approximation, and C, figure C, where it is second approximation. It shows the appearance of the Koch curve after first approximation and second approximation. After every approximation we can see the appearance of Koch curve. After second approximation, the length of the curve becomes 16 by 9 times of the original curve. Did you get it? By each time, like when we have adjusted in the, or we have built 4 equal line segments of the original, we say that the original length is 1 by third, right? So the length of the new curve will be 4 by 3. But in case when we go on doing it, so till second approximation it becomes 16 by 9 times the original length. So after looking at this, we can have some approximation, or we can say that the length of the Koch curve is infinite, and it will go on changing infinitely. The curve doesn't fill the whole area like it was done in the Hilbert's curve. In Hilbert's curve we can see the whole area was covered, each and every square was covered, but that's not the case in Koch curve. Then it doesn't derivate much from the original shape. It changes the original shape, we can see that. And if we reduce the scale of the curve by 3, we find the curve looks just like the original one, but we must gather 4 such curves to make the original. So here we can say that 4 equals to 3 to the power d of f. To finding fractal dimensions, we get n equals to 4 here. So d of f equals to 1.26, and we can say that for Koch curve topological dimension is 1, because obviously it's a line, so topological dimension is 1 and fractal dimension is 1.26, right? So we can say the Hilbert's curve and Koch curve are fractals, as their fractal dimensions are greater than their topological dimensions, right? As we already know that, as we have discussed in fractals, that curves whose fractal dimension is greater than its topological dimension, then they are called as fractals. Did you get the point? Let me repeat once. curves whose fractal dimensions are greater than its topological dimension, they are called as fractals. And so here we can see the Hilbert's curve and Koch curve are fractals as their fractal dimension is greater than their topological direction. In Hilbert curve also fractal dimension, topological dimension was 1 and the fractal dimension was 2. And in here Koch curve also topological dimension is 1 and fractal dimension comes out to be 1.26. So in both the cases fractal dimension is greater than topological dimensions, and so Koch curve and Hilbert curves both are called as fractals. So let me repeat once, what are fractals? Sorry, what is Koch curve, triadic Koch curve, and how to draw it? Triadic Koch curve, basic curve, and for drawing this we have to start with a line segment and then we go on dividing the line segment in 3 equal parts. After that, see, the line is divided into 3 equal parts. So for original length we have considered it as 1 by 3. Did you get it? Then we are dividing that line segment into 3 equal parts, and after that we are replacing the central third part by 2 adjacent sides, right? Often we can say it forms an equilateral triangle. Now in this, after that what we get the new length as 4 by 3, and so on. When we go on doing approximations, that is dividing each line into 3 equal parts again and again, after the second approximation, that is in figure C, we can see we get the length as 16 by 9. And here, so here we can get that the topological dimension is 1 because of it's a line, and fractal dimension here comes out to be 1.26. As n we can take as 4 and the scales of the curve can be 3, these 3. Okay, so this is Koch curve.